Hello, Chem 2. Welcome. I'm excited to have you all back this quarter, and I wanted to start off by letting you all know that this quarter is a little bit more difficult than Chem 1, and that is why this has a 3 credit hour distinction rather than a 1 credit hour distinction. So just to kind of start you off, we do have guided notes that will go with this video to assist you as you progress, and I highly suggest that you print those out prior to viewing the videos. And additionally, it is important that you keep up with memorizing the material from week to week and trying to stay on top of it, as it does snowball quite quickly. As always, I'm available via email or text. Please send them to me as soon as you can, and I'll be able to assist you. So let's go ahead and just get you introduced to what Chemistry 2 is. Well, Chemistry 2 will be focusing on organic chemistry and how we use this in embalming. So the first thing we need to do is just have a basic overview of what organic chemistry is. And organic chemistry is defined as the chemistry of carbon and carbon-containing compounds, and we also call this the chemistry of things derived from living or once living things. And so we really will be studying this throughout. You know these definitions. They are test questions. So these are things that you can easily go ahead and start memorizing and learning from the get-go. So organic chemistry is dealing with these carbon-containing compounds. And so they do have a different naming scheme than what we used in Chem 1, and that is going to be the primary focus on the first half of this course. So let's contrast between Chem 1 and Chem 2 by looking at inorganic versus organic compounds. So there are thousands of inorganic compounds, but there are literally millions of organic compounds. We have so many more, and that's because every additional carbon is going to give us a new compound. Inorganic compounds are mainly not flammable. However, organic compounds really are. And so they have a little bit more fuel resource quality part of them. Our inorganic compounds will have very high boiling points and melting points, while organic compounds are mainly low. And what does this mean? Well, this mainly tells us that our organic molecules will be gases or liquids at room temperatures compared to the vast majority of our inorganic compounds, which would be solids. This is not all true, so there are always exceptions, but just looking at the majority. Inorganic compounds are what we would call salts, and they are soluble in water, while our organic compounds are insoluble, so a lot of our fat compounds, which cannot be dissolved. Inorganic compounds will primarily rely on ionic bonding, while organic compounds will rely on covalent bonding. The inorganic compounds will react between two ions, those are the charged atoms, whereas organic compounds react between what we call molecules. We think of inorganic compounds as simple compounds. It is one ion bonded to another, whereas organic compounds are very complex. They're very, very large, and they have many atoms, which brings us to our last box here. Inorganic compounds are very small in size, very few atoms, while organic compounds are very, very large with many atoms. So remembering that inorganic compounds are written in this molecular formula of C2H6 and O, and this formula here is telling us that there are 2 carbons, 6 hydrogens, and 1 oxygen. And this works very well for inorganic purposes, primarily because it tells us what atoms are present and how many there are. Unfortunately, this doesn't work for the organic compounds, and this is because it doesn't tell us about the arrangement of the atoms. And what we find is that organic compounds don't only rely on the number of atoms, but also how they are arranged. Where are these hydrogens? Where are the oxygens? How are they interacting with one another? And if I change it up, does that change the compound? All of these go into effect when looking at organic compounds. So in other words, the exact arrangement is very important in identifying an organic substance. So here we can see a formula that is used for 2 different compounds. They're actually the exact same. If you look at their molecular structure, going back here, the C2H6 and O, I can see I have C2H6 and an O, but over here I also have C2H6 and an O. These are very different compounds, and they will react very differently in nature. And this is why organic chemistry is more complicated than inorganic chemistry. We must be able to convey to the reader where the atoms are in the molecule and not just rely on that formula C2H6NO to tell the chemist what molecule we're working with. So how do we work around this? Well, we start looking at different ways of writing those compounds. So let's take a look at this. Each of the above substances contain the same elements with the same number of atoms of each element, but they have very different physical and chemical properties. So this is what we would call an isomer. Isomers are multiple organic compounds with the same elements, the same number of atoms of each element, and different physical and chemical properties. These are organic compounds that then have the same molecular formula, but what we call a different structural formula. And just for a point of reference, I'm going to go back here for a moment. This layout, the way I have drawn this is known as a structural formula. And then also here, if I go back even more, this again is your molecular formula. So isomers are when we have the same molecular formula and different structural formulas. So one way that organic chemists will convey different compounds to the reader is to actually draw the structural formula with the molecular formula next to it. So because of isomers, a new formula is created to then show the elements involved and how many of each, as well as the arrangement of the atoms. And so that is the structural formula. This is a diagram, by definition, which shows the exact arrangement and bonding patterns of the organic compound, and that's what I showed you above. So when talking about organic compounds then, it's important to remember the number of valence electrons or the number of bonds possible for some specific elements. So this is a review from Inorganic Chemistry, which is Chem 1, and it's very important that you have these rules memorized. So you should go ahead and make flashcards of these or have them put away somewhere. So these are the 4 that you really need to know. Carbon will have 4 valence electrons, therefore it has 4 places for bonding to occur to other elements. Nitrogen has 5 valence electrons, which means it has 3 places available for bonding to other elements. Oxygen has 6 valence electrons, so it has 2 places available for bonding to other elements. And our last one is hydrogen, and this has 1 valence electron, so it only has 1 place available for bonding to other elements. You don't really need to know the number of valence electrons as much as you need to know the locations or the number of bonding locations for each one of these compounds. This will be very helpful when you're drawing your structures later in this course. So here's another way of looking at it. Carbon will have 4 bonds. Nitrogen will make 3 bonds. Oxygen has 2. And hydrogen has 1. Each of the above must have every bond full in order for this compound to be stable. So when you're drawing your compounds, if any one of these 4 elements breaks the rules, then it is not a possible compound, and you need to fix your drawing. So let's look at how carbons can then bond in these 4 ways. Using this structural formula, we can actually show how carbon will unite with other substances in many ways. So here, carbon will unite with 4 single atoms, and we would actually call this compound methane for reference. More to come on that. Here, we can see that carbon is bonded to oxygen, 1, 2, 3, 4. So in this example, there are 4 bonds, but they're what we call double bonds. Also notice that oxygen can be bonded in 2 locations, and it's also following this rule as well. Here, carbon can unite with 1 what we call divalent and 2 single valent atoms. So again, 1, 2, 3, 4 surrounding carbon. Hydrogen's happy with 1 bonding location, and oxygen is happy with 2. These are the names of our compounds just for reference. Carbon dioxide and formaldehyde. Be sure you know the compound structural form and molecular formula for formaldehyde, as we will be using this quite often for the remainder of the quarter. So let's take a look. Carbon can unite with other carbon atoms in several ways. Here you can see a basic structure with carbon chain, and then we fill in the surrounding areas with hydrogens. Notice every carbon has 4 bonds. They're all single bonded to one another, and they're single bonded to the hydrogens, and everyone is following their rules. Down here with letter B, we actually see a different structure format, where the carbons all again have 4 bonding locations, 1, 2, 3, 4. However, the carbons in the center are double bonded to one another, and therefore they can no longer hold a hydrogen bond because they can only maintain 4 bonds. Our last example is when carbon can have triple bonds. Again, the carbon is surrounded by 4 bonds total, but in between some carbons we have triple bonds. The reason carbon is able to bond in so many different ways is because of its shape, and this is due to geometry, and we would call this its tetrahedral shape, and tetra in Greek means 4. The above drawings show how structural formulas can become complex and then very hard to read. So in some cases, it might be useful to draw the structural formulas. However, in others, this could be tedious. So there is a shortcut that can sometimes be used as a hybrid between a molecular formula and a structural formula. So let's take a look at these compounds below. Here, we're seeing a straight line of our structural formula of many carbons single bonded together. In this structural formula, you have many carbons bonded together, but then here we have what's known as a side chain, which we will learn more about. In this example, we have a primary carbon chain and 2 side chains as well. And this is a very confusing format, and it does have very specific names that we will be learning in this course on how to name these 3 structures. But for now, let's just focus on how we would name this using a semi-structural formula. So a semi-structural formula is that hybrid, or it's an abbreviated structural formula that combines the use of our structured formula and molecular formula. And we do this with repeated symbols that we see often in our structural formula. So here are some examples below. Here you see the C with the 3 hydrogens surrounding it and the CH3. Then we see that C in the center chain with CH2, followed by CH2, CH2, and finally our final CH3. So let's go back 1 page. Here's the example of what I just read to you below. Our first carbon has 3 hydrogens bonded to it. Our second has 2, 2, 2, and lastly 3 bonded to it. So again, our semi-structure shows us the same format, but it gives it to us one at a time. Down here where we see our parentheses, this is showing us our side chains. So here our main chain is not in parentheses, but then our side chains are shown next to the carbon they're bonded to. So what I want you to start doing is I want you to read through chapter 7, complete the week homework, and I want you to start working on the list of prefixes and suffixes shown in the chapter that start with methane, ethane, propane, and butane. These are called IUPAC prefixes, and as you go through them, you should make flashcards and start preparing for those. So if you can go through and start learning your suffixes and prefixes, you'll start getting ahead for the following weeks.